Welcome to our read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 6.2.3, the definition of a determinant. Okay, so if we look back at our work from the last subsection, notice that after distributing like our -2 and our 3 and our 1 into the different parts of the calculation, like we had a determinant calculation 3 times 4 minus 1 times 2 and so forth, we actually get some products. Looks like it's like three things, three things, three things, three things, three things, three things multiplied together. Another way of thinking about this, how to get these products, is simply rearranging. If we rearrange our columns, so this -2, 3, 1 moves around, and kind of the columns move around. And notice as the column moves around, we look at the this diagonal right here only, just in the red, and we multiply that. That actually turned out to be all of these guys, as long as we make some of them positive and some of them negative. That is, some of these permutations right here are of the columns are even permutations, and some of them are odd. Remember what even permutations means. You can even number of switches. Odd permutations would be odd number of switches. The odds we give a negative, and the evens we give a positive to. And if we did that, it actually ends up giving us the determinant. Let's take that as kind of a definition for what a determinant is roughly, at least at this in some way. What we can do is we just do all the permutations we can of the columns. For even permutations, we put a plus, odd we put a minus, and then we just look at the diagonals, multiply them respectively, and attach the signs to it and add it up. And that would work for any size of matrix, 3 by 3, 4 by 4, 5 by 5, and so forth, if we did that. But so notice we have 6 things to add, and that is because this is we're looking at permutation on 3 things, so 3 factorial is 6. If we were doing a 4 by 4 and we did the same technique, there would be 24 different things to add if we had done it this way, and that seems like quite a bit. But nonetheless, we can take that as a definition. Okay. Let's see. Every permutation of columns produces a diagonal. Okay. This is interesting to note. So we could have actually gotten the same result from the calculation by doing rows. Actually, we end up getting the same diagonals, and we can still kind of do it with even and odd permutations. So this whole definition that we did with columns, we could have actually done with rows instead, and it actually gives us the same result. And so that's interesting to note. Okay. All right. Let's take a look at the next subsection as well. Subsection 6.2.4. Repetition yields a zero determinant. Repetition in what? Repetition in the columns. Okay. How is that? Well, think about when you do all your permutations, because you can switch these two, but it doesn't look any different, right? And when you switch, let's see, so let's suppose you have these two right here and these two right here. Notice that there's an even permutation and an odd permutation that keeps these right here, and that's because one of the switches can't be seen. So from an even, if you switch these two, then it's an odd, but you cannot see it, and so therefore it's just right. So the result right here of this product is going to be the same as over here, except there's going to be a positive and negative. They're going to exactly cancel out because you can pair this permutation exactly with one over here. So if there's any repetition in the columns at all, we know we're going to get we're going to have a zero determinant. It's going to zero out completely. Like notice like here and here, those cancel, and here and here, those cancel as well. Okay. So let's now think about how we can use that idea. with what happens if we slide, meaning we add a multiple of one column to another one like this. See these red numbers here? Let's consider what's going on. Well, we can do the same idea for permuting the columns, and then we're going to look at the diagonals, multiply them together. Now, when we do this and we multiply together, notice there's we can distribute as we multiply, and so we can distribute across. So we can distribute across like this addition here, this addition here. Let's see this addition and so forth. We can kind of do when we do that and separate out the parts, we can actually separate the parts that contain red, that contain the red. Now, notice when we do that, then it's as if we were considering just having the red here in this column 1, 4, 3, and we know that determinant is 0. So we can actually ignore all the reds, meaning that we don't have to worry about them in the determinant calculation, because after distributing, we're going to have a determinant type result with where all the reds, whereas if we were just considering this case right here with repeating columns, and we know we're going to have 0, so we may as well just ignore the reds and just have the blacks here, which in these numbers, which means that that it didn't matter. It doesn't change the determinant when we slide, when we add by a multiple of another column. It does not change the determinant at all. So we kind of get a sense for it's the exact same thing as we were thinking of for oriented volumes and areas. It doesn't change anything by sliding. It even works not only visually, but even just generally with that more general definition of a determinant. So sliding does not change the determinant. Sliding meaning you add a multiple of one vector or one column to another. In the next subsection, we're going to actually be using this idea to compute the determinant just with mere sliding. Thanks for watching.